Thank you, Jennifer, for the introduction. So hello, everyone. My name is Mojtaba. I'm from Leuven, Belgium. My presentation is related to my PhD work on mathematical modeling of degradation process of metallic biomaterials in various setup conditions. So I start with a very general introduction of biodegradable metals. Talking about biodegradable metals, we are usually referring to magnesium, zinc, and iron. And the functionality is they gradually disappear and get absorbed and replaced by absorbed by the body and get replaced by new tissue and bone. And they have great mechanical properties because they are metals and they have positive contributions to the human body metabolism. But at the same time, the control release profile is an issue for different applications. And it should be tuned to the rate of, for example, tissue growth or get optimized for various applications. As an example, for example, as a use case, I can tell you about 3D printed acetabular implants, which is indeed the objective of my PhD work. That in the end of their lifetime, these implants should be replaced by new ones in a revision surgery. But the problem is extra bone is also removed along with the implant during this revision surgery, making it difficult to achieve further mechanical stability. But one of the solutions to this is making at least part of the implant from biodegradable metal. But this requires tuning the biodegradation rate to the rate of regeneration of the new tissues. This is actually solved in this project by constructing a mathematical model of biodegradation process and coupling these biodegradation models with tissue growth models, and also considering the effects of the environment. The modeling workflow in this project is converting underlying sciences to mathematical models and then mathematical models to computational models. The underlying sciences in this project are the chemistry of biodegradation, the physics of perfusion and perfusion setup, which is actually fluid flow, and also biology of tissue growth. For constructing the mathematical models, we take advantage of partial differential equations, namely reaction, diffusion, convection equations, and Navier-Stokes equations for fluid flow, and also level set method, level set formulation for tracking the change of morphology. And the computational models is actually a combination of finite element method and finite difference, scientific computing libraries, as well as open source solvers. So a very quick overview on the chemistry of biodegradation. It's actually a complex phenomenon from the chemical perspective, but the model should capture the dissolution of metallic implants and then a formation of a protective film, as you can see here on a surface of the material, and the effects of various ions in different solutions and change of pH. And then a mathematical formulation can be constructed based on these by converting the chemical interactions into mathematical forms by using reaction, diffusion, convection, partial differential equations. In my model, I have 6 to 7 equations, but as an example, I will demonstrate the equation for the dissolution of magnesium. This is more or less a mass transport equation. So it has the fusion term, the convection term, the effects of fluid flow, and also the reaction term showing that how it reacts with different components, with other components in the solution. And then the next step is constructing the computational model. It's not feasible to implement this kind of mathematical frameworks in sophisticated software programs like Abacus or ANSYS. So we had to discretize the differential equations ourselves using numerical computation. So finite difference method for time derivative terms, for temporal terms, and finite element method for spatial terms. And the mesh is something like, it's a multi-material mesh. So we refine the interface, we label the mesh with the computational domains into 2 domains, the implant and the surrounding medium. And then we refine the interface, refine the mesh on the interface to increase the accuracy because we want to capture how this interface evolves. So actually, this is a sort of moving interface problem. For the immersion case, which is a sort of stationary case that we put materials inside a solution, and when they want to see what happens during the degradation. I have a narrow cuboid of magnesium in simulated body fluid and saline solutions, and the goal was simulating 21st hours of degradation to validate the model. And then the mass loss was indirectly measured during the experiments and also during the computation by the formed side corrosion products, in this case hydrogen, and the global pH is monitored and used to validate the model. So this is actually the initial results that we have. You can see on the left the release of magnesium, these red spots, and also these white regions are actually the implant or the material block or the medical device. In this case, it's a narrow cuboid. So as you can see, a narrow film is formed on the interface, and as the material is released. And this is an animated demonstration of that. You can see both are the same, but with different techniques for visualization. Height evolves, and you can see that the solution and the corrosion process of magnesium. And then I have the change of pH, as I told you, for validation. On the left for saline solution, high diffusion rates, and on the right for low diffusion in simulated body fluid solutions. And these are quantitative results. And as you can see, the references are already published for the site corrosion products and change of pH, and a very good agreement between the computational and experimental results. But also, as I said in the beginning, also for perfusion case, because in tissue engineering, it's a very common setup to have the perfusion, which means literally means having fluid flow to provide the nutrients, oxygen supply, this kind of stuff. It's very common to have this. So this model should be also capable of simulating that, capturing the physics behind. And for doing that, we need to add fluid flow simulation, sort of computational fluid dynamic simulation to the model. And then we consider degradation inside this chamber with an inlet on the left and an outlet on the right. But then an issue is we want to make sure that the CFD code that we have developed works correctly, because it became very costly if we wanted to combine it with already available CFD codes. So costly from resource utilization and time. So we developed our own CFD code, and this is the comparison of the fluid results between our in-house code and OpenFOAM, the famous CFD solver. You can see the magnitude of velocity is almost the same. Also the streamlines from the side view, and also streamlines from the top view. And this is also an animation of what happens if the degradation occurs along with fluid flow. You can see that it moves the release materials, and also it's a sort of directional degradation. But actually, this is an ongoing work, so I don't have quantitative and also validation results on this part of the work yet. The developed code and employed tools are all open source. The source code of the codes that I have developed are all available on GitHub. And as I told you, all the employed tools are also open source. The tools that I use for solving the equations, for parallelization, for solving PDs, and also mesh generation, CAD design, they are all open source, meaning that if you grab the code, if someone was interested in using my code, they can easily grab the code, and all the prerequisites are all also open source. As a conclusion, I can say that this work presented a quantitative or semi-quantitative mathematical model to assess a predicted biodegradation behavior of metallical implants. And then the capturing fluid flow is as important as capturing the immersion tests set up for capturing hydrodynamic conditions. And in the end, by predicting biodegradation behavior, this can be an improvement on a general and overall workflow of designing biodegradable orthopedic implants. So thank you so much for your attention.